In this video, I'll be reviewing concepts from section 8.2, System of Linear Equations in 3 Variables. So first of all, if you remember from the first video, we looked at systems of equations in 2 variables in which we had 2 linear equations that when graphed would give us lines that possibly intersected, and the point of intersection is where we would find our solution for x and y. In this example, or in this system, we are looking at systems of linear equations in 3 variables. So not only do we have an x and a y variable, but now we also have a z variable. And when we graph equations that include 3 variables, we no longer get linear equations. So this should just be systems of equations in 3 variables, because we're no longer dealing with a linear line, we're actually dealing with a 2-dimensional plane. So when you have an equation in 3 variables, you get a 2-dimensional plane, and the point in which the equations intersect, or the planes intersect on a graph, is going to be your solution point. And you're going to get an x and a y and a z variable. So there will be 3 solutions to a system of equations in 3 variables. Now we call this an ordered triple because there are 3 variables in this point where the planes intersect. So in this first example, I have a system of equations in 3 variables, and that means I have 3 variables for each equation. I have variable x, y, and z, and I want to find that solution, that ordered triple that will satisfy all 3 equations. So this is my system of equation. So to find out if the ordered triple here of 1, 0, 2, so when x is equal to 1, y is equal to 0, and z is equal to 2, to see if this is the solution of this system of equations, we're going to substitute those values into each of these equations. So our first equation is here, and you can see that we put x, y, and z values in, and when we simplify, we get a true statement. So far that ordered triple does satisfy the first equation. Looking at our second equation, we again substitute the values of 1, 0, and 2 in for x, y, and z, and you can see that the statement is true. And you can't assume that just because it works for 2 of the equations that it's automatically going to work for the third. You still have to go through the motions. And you can see that in the third equation, when we substitute those values in for x, y, and z, we do end up with a true statement. So this ordered triple is the solution to this system of equations in 3 variables. So what we're going to do is we're going to solve a system of equations, and this is our system of equations in 3 variables. And we're going to use substitution and addition method, just like we did when you had a system of equations in 2 variables. Now it takes a little bit more steps because we do have 3 equations and 3 variables. First thing I'm going to do is I'm going to label my 3 equations, and then I'm going to take equation 1 and equation 2, and using the addition method I'm going to eliminate one of the variables. So 5x minus 3y plus z equals 2, and 2x minus y minus z equals negative 3. And I can see here that I can eliminate my z's just by adding these 2 equations together. And what I get is 5x plus 2x equals 7x. Negative 3y plus negative y is going to give me negative 4y. My z's cancel out, and 2 plus negative 3 gives me negative 1. This becomes equation 4, and equation 4 only has 2 variables, x and y. So I'm going to use that later. My next step is I'm going to do the same thing that I did to equations 1 and 2, but this time I'm going to use equations 2 and 3. I'm going to get equation 2 is 2x minus y minus z equals negative 3, and equation 3 is x minus 2y plus 5z equals 12. Now the key here is that you have to eliminate the same variable you eliminated in the first step. So if I eliminated z in this step, I also have to eliminate it here. So I don't have a choice. I have to get rid of my z's. Now if I have positive 5 here, I need to add negative 5 in order to get rid of that z. So I'm going to multiply that z variable by 5, and whatever I do to that variable, I have to do to all of the variables in the equation. So I'm multiplying all the coefficients in equation 2 by 5. So my new equation will be 5 times 2 gives me 10x, 5 times negative y gives me negative 5y, 5 times negative z gives me negative 5z, and 5 times negative 3 gives me negative 15. This is my new equation for 2, and I'm going to add it to my original equation for 3. And you can see that negative 5z plus 5z, those are going to cancel out. So when I do add, I get 10x plus 1x is 11x. Negative 5y plus negative 2y is going to give me negative 7y. My z's cancel out, and negative 15 plus 12 is going to give me negative 3. Now this new equation is going to be equation number 5. My next step is to take equation 4 and equation 5 and eliminate one of the variables, so I'm just left with one variable. So here I'm taking equation 4 and equation 5, my new equations that only have two variables each, and what I'm going to do is I'm going to eliminate y. And I'm going to do it by the addition method. But first of all, I have to multiply this first equation by 7 and this second equation by negative 4, because that's going to help me to eliminate y. Watch what happens when I multiply all the coefficients in equation 4 by 7. So I get 7 times 7x is 49x. 7 times negative 4 is negative 28y, and 7 times negative 7 gives me negative 7. And then I'm going to multiply all of my coefficients in equation 5 by negative 4. So negative 4 times 11x is negative 44x. Negative 4 times negative 7 gives me the positive 28y that I needed. That's why I had to include that negative 4, because I had to change this to be positive in order to eliminate my y's, because negative 28 plus positive 28 is going to do that. And then lastly, negative 3 times negative 4 is positive 12. Where students go wrong is that they will mess up on the signs and they won't get the right equation when they go to add them together. So now I'm going to add them together. I get 49 subtract 44 is going to give me positive 5x. My y's cancel out. The negative 28 plus 28 gives me 0. And negative 7 plus 12 gives me positive 5. Then to solve for x, I'm going to divide both sides by 5, and x is equal to 1. So I've just solved for my first variable. Next, what I want to do is I want to take that x equals 1 and substitute it back into equation 4. And by doing that, I can then solve for y. So 7 times x, which is equal to 1, minus 4y is equal to negative 1. 7 times 1 is 7, minus 4y equals negative 1. I'm going to move my 7 over to that other side. That's going to give me negative 4y is equal to negative 1 subtract 7, which is negative 8, and then divide both sides by negative 4, and y is equal to positive 2. And now I've solved for my second variable. Now my last step is to zoom out a little bit and take my new x value and my y value and substitute it into my first equation to solve for z. So I'm going to take, oops, give myself a little bit of room. And I'm going to take my first equation, 5x minus 3y plus z equals 2. I'm going to substitute 1 in for x and 2 in for y, and then I can solve for z. Oh. So 5 times 1 is 5, negative 3 times 2 is negative 6, plus z equals 2. 5 subtract 6 equals negative 1, plus z equals 2. I'll add 1 to both sides, and I get z is equal to, oh, that should be a 2. Z is equal to 2 plus 1, which is equal to 3. Z is equal to 3. Now I've solved for all 3 variables, and if I wanted to do a check, I would put this new tripled order triple, which is going to be 1 for x, 2 for y, and 3 for z, ordered triple, and I would check to make sure that that satisfied equation 2 and equation 3 to make sure that I was on the right track. But that is the solution if I were to check it to those 3 equations. And my last example is again solving a system of equation in 3 variables, except this time one of my equations is missing a variable. My equation 1 is missing that y variable. So in this case, what we're going to do, I'm going to move this over a little bit. I'm still going to label my equations 1, 2, and 3, but this time I am going to take equation 2 and equation 3, and I'm going to add them together to eliminate the y variable so that they're similar to equation 1. So equation 2 is x plus y plus 2z equals 17, and equation 3 is x plus 2y plus z equals 16. I do want to get rid of my y variable right here, so that means I'm going to multiply all of my coefficients in this first equation by negative 2. So my new equation is going to be negative 2x subtract 2y plus, oh, not plus, negative 4z equals negative 17 times 2 is going to be negative 34. And then equation 3 is x plus 2y. That's going to eliminate my y's, which is great, plus z equals 16. And I am going to add these two together. So negative 2x plus x is going to give me negative x. My y's cancel out, and then I have negative 4z plus z will be negative 3z, and negative 34 plus 16 is going to give me negative 18. This is going to be my new equation 4. Now what I'm going to do is I'm going to take my new equation 4 and equation 1, and I'm going to add them together to eliminate one of the variables, since I only have 2 variables in both of those. So I'm going to take equation 4 and equation 1, which is x plus z equals 8. And you can see that I don't have to do anything to that equation 1. I just have to add them together, and my x's will cancel out. And that's going to give me negative 3z plus z is going to give me negative 2z, and negative 18 plus 8 is going to give me negative 10. And then I can just divide both sides by negative 2. That's going to leave me with z is equal to positive 5, because negative 2 divided by negative negative 10 divided by negative 2 is positive 5. Now that I've solved for one of my variables, z equals 5, I'm going to put that back into equation 1 and solve for x. So back into equation 1, I have x plus z equals 8. So I'm going to solve for x when z is equal to 5. X is going to be equal to 8 minus 5. So x is equal to 3. There we go, x is equal to 3. Now that I have x and I have z, I'm going to take equation 2, which is x plus y plus 2z equals 17. I'm going to input 3 for x and 5 in for z, and solve for y. So that's going to give me 3 plus y plus 10 equals 17. 3 plus 10 is 13 plus y equals 17. Subtract 13 from both sides, so 17 minus 13. And then y is equal to 17 minus 13, which is equal to 4. So y is equal to 4. And when we substitute that x, y, and z value, which is our ordered triplet, so our solution is 3, 4, and 5, that ordered triplet satisfies all 3 equations. So that's how you solve a system in 3 variables or 3 equations when you have a missing term. So practice makes perfect. These ones take a little bit of time and a little bit of patience. But good luck, and thank you for watching.